And okay, thank you. Continue. This is joint work with my PhD supervisor, Professor David Manlove, and a brief outline of what I'm going to be talking about. So the research is on matching problems, and I'm going to be zoning in on the student project allocation problem, which divides into 3 to 4 branches. And I'll briefly introduce some of the problems, the existing techniques, and my own results, and tie it in all together at the end. So without wasting much time, matching problems, that's the um, body of the whole research I worked on during my PhD. And it arises when we seek to assign a set of entities to another set of entities. So when you have a problem where people have preferences over one another, and there is some form of capacity constraint involved, then matching problems naturally arise. So the problem was first studied in 1962 by Gale and Shapley, and the result was presented in their paper titled The College Admissions and the Stability of Marriage. And the college admissions models the problem of allocating applicants to colleges, while the stability of marriage models the problem of matching men to women. And in all of the applications, the goal of the problem is to match the two entities to one another in such a way that no one would be unhappy with what they have and the matching would unravel. So we call that stable matching. And ever since the paper was published in 1962, there has been tons of research in the areas of matching problems, mostly inspired by practical applications. And some of those applications, the kidney exchange problem. So we have a situation where Diana needs kidney and Jim, her dad, wants to donate his kidney to Diane, but they are incompatible. And a family somewhere, Bob and Alice, wants to exchange kidney, but they are not compatible. However, by swapping the kidneys around, the exchange can still take place. So this is known as the kidney exchange problem and modeled as the matching problem. And this application is going on extensively in the UK. So my supervisor is leading the team that works with the NHS. And on a yearly basis, the NHS uses the algorithm they designed to find optimal swaps between kidney transplant patients and their incompatible but willing donor. And another application is the hospital's residence problem, which involves residents who wish to be assigned to hospitals for their medical residency programs. So the hospitals have preferences over the residents that find them acceptable. And they also have a notion of capacity, which tells us how many residents they are willing to accommodate. And the residents also have some form of preference over the hospitals, perhaps based on location or the kind of medical residency program they want to undertake. And this has also found very wide applications. I think the largest is the National Resident Matching Scheme in the United States. And annually, they assign up to 40,000 residents to hospitals. There is also the Canadian Residence Matching Scheme in Canada and the Japan Residence Matching Scheme, among many others. And another application is the Student Project Allocation problem, which is where my research is based. And it involves students, projects, and lecturers. Lecturers propose projects, and the students choose some of these projects that they find acceptable, maybe up to a fixed length, depending on the department under consideration. And the lecturer also have some form of capacity constraints over the project and over themselves as well. And the problem is to assign students to projects based on the preferences and based on the capacity. So underlying all of these matching problems, the very fundamental model that is used to solve them is graph. So we model each of these as a graph. For example, in the hospital residence problem, the residents are the vertices. The hospitals are also the vertices, and there's an edge connecting one resident to another hospital if the hospital appears on the residence preference list. So the language we speak in matching problems is literally graph. However, based on the kind of problem we are dealing with, we can classify matching problems into two. So we have non-bipartite extension and bipartite. For the kidney exchange, it's a non-bipartite graph model. And for the hospitals residents, it's bipartite with two-sided preferences. And what that means is that both the residents and the hospitals both have preferences. However, for the house allocation problem, The applicants who wish to be assigned to houses are the only one that have preferences. The house doesn't have any preference over the applicant. So that type of matching problem is a bipartite, one-sided matching problem. So my talk for today is going to be under the two-sided preferences, which falls under bipartite matching problem, which is the student project allocation problem. So the SPA problem, for short, involves students, project, and lecturers, as I've said before. The lecturers propose the project, the students provide preferences over the project, and there is the form of capacity over project and lecturers, which is decided by the lecturer that proposed the project. Now, in several variants that have been studied in the literature, one thing that is fundamental to all SPA problem is that the students always have preferences over projects. Of course, they have to do. So the students have preferences, but then lecturers may not have any form of preference. So this extension of SPA is actually what is being used in my school, the School of Computing Science at the University of Glasgow. Every year, to assign the level 4 students to projects, the students have preferences over the project, but the lecturers don't provide any form of preference. And there is also the application where the variant where the students have preferences over projects and lecturers have preferences over the students that find their project acceptable. And this has been applied, I think, at the Department of Math, University of York. And another variant is a SPA-P. So in these variants, the students have preferences over projects, and lecturers have preferences over their proposed projects. And this arises in a situation where lecturers might be expected to produce, say, up to a certain number of projects. However, some of these projects are closely related to their current area of research, and they would rather supervise those to some other projects they propose just to meet the capacity constraint. So we have the SPA-P, and then we have the SPA-SP, which is the hybrid of SPA-S and SPA-P, where lecturers can have preferences over student project pairs. Now, in all of these variants, one thing we seek is a matching, that is allocation of students to projects that respects the preferences involved and the capacity. And for my talk, I'm going to be focusing on the SPA-S and the SPA-P. That's the student project allocation, where students have preferences over projects and lecturers have preferences over students, or they have preferences over the project, but not the two at the same time. So next, I'm going to be looking at SPA-P first. So this is a very simple instance of SPA-P. To the left, we have the student preferences, and to the right, we have the lecturer preferences. And below, we have the project capacity. So all of the projects have capacity 1, and the lecturer 1 have capacity 2, and lecturer 2 have capacity 1, and that's what this means. And the arrangement of the student preferences just means that student 1 prefers project 3 to project 2, and she prefers project 2 to project 1. And for the lecturer 1 prefers project 1 to project 2. So that's how to interpret the instance in front of you. And based on what I said earlier, we would like to assign, would like to find a matching. So this is a matching. However, this is a matching because each student is assigned to one project, and no project capacity is exceeded, no lecturer capacity is exceeded. Even though S3 wants to go to P3, it's already been given to another student. So this is a matching. However, student 2 would like to be assigned to project 1, as you can see based on the preference structure. And the lecturer that is offering project 1 as well would prefer project 1 to what they've currently been assigned. So the two form a coalition, S2 and P1, we call a blocking pair, because the student and the lecturer would be better off by swapping their project to the new project. And naturally, we say we want to avoid these kinds of pairs in our matching. There's no point going through the stress of finding a matching and then some student and lecturer form a blocking pair or form a coalition. So we say that we want to avoid blocking pairs in our matching. But then again, yeah, this is a definition of blocking pair. Don't worry yourself about the details. This is just for completeness. For a blocking pair to occur, a project must be undersubscribed, and there are 3 different conditions that can lead to a blocking pair. Now, this is another matching where there are no blocking pairs. You can verify that quickly. S1 wants to go to P3, the lecturer is full. The lecturer is indifferent between the students anyway, so they can't form a blocking pair, same as S1 P2, same as S2 P1. So there are no blocking pairs here. However, you will see that by moving S1 to P2, S2 gets her favorite project, which is P1. So these two students would form a coalition and then swap their project around. So that could piss off the lecturer because maybe they've started working with the student and the student realized that they want to swap around. Just to avoid any form of unraveling in our matching, we also want to avoid coalition. So a very brief definition of coalition, and to make it very clear, imagine we have all the set of students listed here in such a way that we draw a directed edge from one student to the next if S1 envies S2 project, and a directed edge from S2 to S3 if S2 envies S3 project. And that keeps going until we get a directed cycle. So if we have this structure in our problem, then we say that the solution admits a coalition. So this is the simple definition of the coalition. So what type of matching do we seek? Essentially, we seek a matching that admits no blocking pair and no coalition because we don't want to piss off the person allocating students to projects. So we say a matching is stable if it has no blocking pair and no coalition. Now, based on that definition I just gave, no blocking pair, no coalition, this is a stable matching. S1 and S2 are fine. They are assigned to their first choice project. The only person that can make this unravel is student 3. Student 3 wants to be assigned to project 3, but then again, the lecturer is happy. They have their project and they are indifferent between the students, so that doesn't form any blocking pair or coalition. And again, we have another matching. No blocking pair, no coalition. So this is two different stable matching with two different sizes. Clearly, the first one matched 2 students and the second one matched 3. So a natural question we would ask ourselves is, how can we find a stable matching that matches as many students to project as possible? And that leads to another problem, a maximum cardinality stable matching. Given an instance of SPARP, can we find a maximum cardinality stable matching? Because in practice, we would want to match as many students to project as possible. So this problem apparently is NP hard, and there are existing approximation algorithms in the literature. And the first one guarantees us at least half the size of the optimal solution. And the second guarantees at least 2/3 the size of the optimal solution. And now the natural question is, can we do better? What can we do to make sure that we're able to find an optimal matching in practice? And the answer is yes. A technique we can use is known as integer programming. And even though IP problems are, naturally NP hard in practice, in theory, IP integer programming is NP complete, I think. There are known solvers, for example, Cplex solver, Gurubi, that are being designed with sophisticated, state-of-the-art softwares that can solve some integer programming problems to in a reasonable time. So the approach we took next was to construct an integer programming model for the problem of finding a maximum stable matching in SPARP. And very briefly, to construct the model, same as all IP problems, what we need is a set of binary variables, a set of constraints, and an objective function. So for our problem, we created binary variables to mimic the assignment of students to projects. And then we enforced 3 different types of constraints: a matching, no blocking pair, no coalition. And then the objective function is just to maximize the size of the matching. So I'm going to go through this one by one with a very nice instance, just so you have a feel for what the model looks like. So for this instance here, the first thing we want to do is encode the variables to represent the assignment of students to projects. And what we use is zeros and ones. So 0 is going to mean a student is not assigned to the project, and 1 would mean the student is assigned to the project. What do I mean by by that. So for instance, Xij here, for each student, this is S13, S12, and S11. So X13 is going to be 1. If it's 1, then we know that S1 is assigned to P3. So S13 is the variable representing student 1's assignment to P3. And if it's 0, then we know that S1 is not assigned to P3. So we do this for all of the students. We encode all of their projects into a binary valued variable. And that's that about the binary variable. It's all done. So the next thing is we have a set of constraints we need to define. And the first one is the matching. So how do we define a matching? Each student is not assigned more than one project. That's the first condition. And to encode that for each student, so this is this AI represents each student, and this Xij sums all of their projects, where it has to be less or equal to 1. So that encodes the condition for that. And for each project, the capacity is not exceeded. So we grab all of the variables representing students that want the project. So for instance, project 1 here, S1, X11, and X21. Those are all the variables that correspond with project 1. And the capacity of that project is 1. So by summing them up, they must not exceed 1. That's the constraint for the project. And for the lecturer as well, we sum up all of the variables of the student and projects that want the lecturer's project. So for here, it's P1 and P2. So we just grab all of the variables where P1 and P2 appear, sum them together. They must not exceed the lecturer's capacity, which is 2. So that is the constraint for the matching. And the next thing is the constraints to ensure that the matching we obtain does not admit a blocking pair. And this is the example, the first example I showed where the instance admitted a blocking pair. And the blocking pair here is S2P1. So we want to make sure that if there is a blocking pair, then that the variable representing that blocking pair with respect to theta ij is 1. Okay, so I'm going to confess a bit, it's going to get heavy. There's going to be a lot of, mathematical jargons on the streets, but I won't delve into too much details. And the next thing is we enforce a variable to hold whether a project is undersubscribed, because the only way a student can form a blocking pair with a project is for that project to be undersubscribed. So we enforce the variable this way, and if this alpha j is 1, that means that the project PJ is undersubscribed, and if it's 0, then it's not undersubscribed. So this equation enforces that. And the next thing in this case is to check if the student is already assigned to a project offered by the lecturer. For here, remember we have 3 definitions of blocking pair. The first one is that, okay, fine, the student wants to be assigned to the project, 1. Next, the project is undersubscribed, 2. Next, is the student currently assigned to something the lecturer is offering? Because S2 is currently assigned to P2. P2 is offered by L1, and S2 wants to go to P1. P1 is offered by L1. That's a very nice blocking pair. So what this gamma ijk encodes is to check if S2 is currently assigned to something L1 is offering. And in this case, it's going to be 1. So we add up all those 3 variables, and we make sure that they are less or equal to 2. Because if they sum up to 3, then we have a blocking pair. So the constraint is to make sure they don't sum up to 3. And then the remaining blocking pair constraints here are for the remaining definitions we have. So that's the blocking pair constraints all done. And the next one is the coalition constraint. But how do we enforce constraint for coalition? We just use the nice model that the coalition has. So for instance, in this problem, we have 3 students, and let's start with student 1. So student 1 wants to go to P2. P2 is offered to S2, so that means student 1 envies S2. Similarly, student 1 wants to go to P3. So student 1 likes at least 2 projects to what she has been assigned. So we draw an edge from a student to another student if the student envies the other student. So we say a student envy another student if they would like to be assigned to what that student has. So here we can see that after drawing this envy graph, we have a directed cycle. So what that directed cycle is telling us is that there is a coalition in our solution. And we know that if a graph admits a topological ordering, then it is acyclic. And if a graph is acyclic, then we already know it doesn't have a coalition. So that is how we enforce our coalition constraints. We define a variable to hold each vertex in the topological ordering, and then we create an integer binary variable to enforce that our graph, our NV graph, admits a topological ordering. And this is the constraint to ensure that that holds. And that's all about the constraints. So the last thing we have to tidy up our IP model for SPA-P is the objective function. And the objective function is just a maximizing function that assigns students to projects. And that's all about the IP model. So we have our variables, we have our constraints, and we have our objective function. And we put all of this together, we solve it, and the solution we get there, we model. So each of the students that is assigned to a project would be one. So the solution, we convert it back to our SPA-P solution, and we find our optimal solution. So this is one of the results from my research. And yeah, this theorem is just saying that if we model the IP, if we model SPA-P using this formulation I just described, an optimal solution in the IP model corresponds to maximum stable matching in the SPA-P problem. And yeah, that concludes the SPA-P. But the next thing we did here was to see how the IP itself, the solution from the IP model, and the solutions of the approximation algorithm. So we ran experiments to see if the bounds on the approximation algorithm is actually as worse in theory as it is in practice, because it's at least half size of optimal and at least 2/3 size of optimal. So we ran experiments to see how well, you know, this approximation algorithms actually performs now that we have something that can give us the optimal solution. So we implemented the IP model using the Gurubi optimization solver, and the aim was just to see how the solution produced compares to the optimal solution. However, when we ran the IP solver on instance of 1,000 students, we realized that it was quite slow when the constraint for coalition was enforced. So we removed this. We removed the constraint for coalition because if you remember, when the coalition exists, after it's resolved, the size of the maximum matching remains the same. It doesn't change. It's only a blocking pair that can change the size of a maximum matching. So, and our aim was just to measure the sizes of the matching obtained from the approximation algorithm and the IP model. So we removed the coalition constraints just to speed up the experiment. And yeah, so the experiment, this is randomly generated SPA-P instances. The line of the one, you can see that as the optimal solution, because this is a ratio of the solution obtained from the IP model and that of the approximation algorithm. So here we have the two approximation algorithm, and here we ran it 100 times. So we ran it 100 times because the approximation algorithms are randomized by design. Depending on the students that is being selected when a project or when a student apply or when a lecturer rejects a student, depending on how the algorithm decides this, the sizes of the solution can differ. So we ran it multiple times, and then we took the biggest of all the runs, just so we are not restricting ourselves to a small maximum matching produced on the first run. So the first run is what we have here. The second run of the 2 approximation algorithm is here. And on top here, we have the 3-on-2 approximation algorithm. But obviously, they are performing very nicely and better than the theoretical bounds. And the next thing we did was to also check if this remains the same when we increase the length of the preference list. So this here, the preference list length was increased from 2, 3, up to 10, and the outcome is still pretty much what we had in the other cell. We can see that there is a closeness of the approximation algorithm produces solutions that are close to that of the optimal solution. So we also ran an experiment using real data sets. So what we had here were randomly generated, we manipulated the data set from the School of Computing Science. Remember I said we run SPA where students have preferences over projects, but there are no lecturer preferences at all. So what I did was create the lecturer preferences in a way from the students' preferences, but at least half of the instance was still real, and the lecturer side was manufactured. So what we also encountered was that the approximation algorithm were producing solutions that are really close in size to the optimal matching. And yeah, they were really performing well. And we would worry that how well does the IP solver scales in practice, because the IP problem is NP complete anyway, but the solvers can produce solutions in a reasonable amount of time depending on the scale of the problem. So we're able to run experiments which produced the results in less than 3 seconds in 100 seconds for size of 10,000 students. But remember, this is the one where we did not enforce the coalition constraints. So coalition can be dealt with in polynomial time by just finding directed cycles in the graph and then swapping the students' choices around. That can be dealt with in polynomial time better than having a stock in the IP solver, which is brute force. It's just some nice optimization technique going on behind the solver. So that's the discussion from the experimental results. And for open problems, theoretically would be, can we design other approximation algorithms with improved bounds for these same problems? And how about FPT algorithms? Is there a parameter of the problem that can be used to design, FPT algorithm? And for these, so if each project and lecture has capacity 1, we know the problem is NP hard. And if each preference list are of length at most 3, we know the problem is NP hard. I proved this. And if there are constant number of lecturers, for instance, if there are 2 lecturers, if there's 1 lecturer, it's solvable in polynomial time. But if there are 2 lecturers, the problems remain NP hard. So what this means is that all of these parameters where the problem remains NP hard cannot be used to try and construct FPT algorithms. So it remains open to see if there are other parameters of the problem. For instance, maybe the total length of the student's preference list or the maximum capacity of the project that can lead to construction of FPT algorithms for the SPA-P problem. So that's that about SPA-P, and I'm just going to let you digest that for like 5 seconds, and then I'll move on to the next problem, which is SPA-S. That's a lot. I've been doing this for years, so I can imagine if you need a bit of break. Okay, so on to the SPA-S problem. Earlier we saw SPA-P, which is the case where lecturers have preferences over projects. And here, it's the case where the lecturers have preferences over students, as you can see on the screen. And the lecturer capacities are here in square brackets. So lecturer 1's capacity is 2 and project 1's capacity is 1. And again, what we seek here is a stable matching. So this is an example of a matching that is not stable. Student 2 wants to be assigned to project 2, and the lecturer offering project 2 would rather have student 2 to somebody that is currently assigned to her. So they both form a blocking pair. And we say that we want to avoid blocking pair at all costs in our matching, again, just so that it doesn't unravel. So what we seek is a stable matching, and a stable matching admits no blocking pair. And every instance of SPA-S admits a stable matching. And this follows from the results in the 1962 paper. And there's a linear time algorithm for the problem of finding a stable matching in the SPA-S instance. And this is published in the paper by Abraham, Irving, and Manlove in 2007. Now, something interesting about SPA-S and all other problems similar to SPA-S in the literature is that there could be more than one stable matching. So there are there is a possibility that an instance of SPICE would have many stable matchings, although there is always one stable matching that is optimal for the student. As you can see here, the red stable matching, all of the students have their first choice. So there is always one that is student optimal, but there could be many more with different properties. So that brings about the question, does the set of all stable matchings have some form of structure? Like, is there a relationship between the stable matchings? And the answer is yes. It forms a distributive lattice under the dominance relation order. And this was studied by Donald Knuth in 97 under the context of the stable marriage problem. It was also studied by Gosfield and Irving in their book, The Structure of Stable Matchings. So what I did was try to solve the same for SPICE. And forewarning, there's going to be a little bit of content coming, but don't read, just listen to me. I have just put them there for completeness again. All right, so what we have here is definition of a dominance relation, because a distributive lattice exists for a set under a dominance relation order. So for us, we define a dominance relation in SPICE as this relation, this precede relation, and we say that a matching dominates another matching if each student prefers it to the other or they are indifferent. So for instance, the red matching here dominates the blue matching because everyone would prefer this red matching to this blue matching. That's definition of everything you have here in front of you. So we say that if we have a set of all the stable matchings coupled with the dominance relation we define here, it forms a partial order. And it's a partial order means it's reflexive, it's anti-symmetric, and it's transitive. So it forms a partial order. And our goal is to show that that partial order is a distributive lattice. But what is a distributive lattice? Big definition coming up. Distributive lattice is just, so we have a set and we have an order on the set. If we have two elements of the set such that they have a greatest lower bound known as meet, we have two elements such that they have a least upper bound known as join, and we have two, the join and the meet relation distribute over one another, then we say that that set is a distributive lattice. So what I did was to prove that the partial order, the set of all stable matchings with respect to the dominance relation, forms a distributive lattice. And I showed that the meet of any two stable matching is also a stable matching. The join of any two stable matching is also a stable matching. The join operation distributes over the meets, and the meet operation distributes over the join. And this is in chapter 3 of my thesis, which you can find at this address if you are interested in the theory. So I proved this, and that was how we're able to conclude that the set of stable matchings in an instance of SPICE forms a distributive lattice. But not to bore you with the theory, I have a nice picture here to tie everything in. So this is an example of a SPICE instance, and there are 12 students, 4 lecturers. The capacities of the lecturers are right here, and the project are here. But you don't even need to worry about that. What you need to know is that this instance has 9 stable matchings, where the first one, M1, is the best for all of the students. It's the one that the student would prefer because they have their best project. So this instance has 9 stable matchings. And because of what I just proved here, that the dominance, the set of all stable matchings form a distributive lattice, we can draw a picture that represents how these stable matchings interact with one another. So the M1 we have here is the student optimal matching. It's at the top. And then M2 and M3. So what this means is that M1 dominates M2 and M1 dominates M3. However, the meet of M2 and M3, the meet goes up, gives us M1. So what that means is that, very briefly, if we look at this, M2 and M3 here, for instance, student 1 is assigned P3 in M2, P5 in M3. But in M1, she's assigned P3. What that means is that P3, S1 prefers P3 to P5. And we can verify that by looking at the instance. Yeah. So the meat of M2 and M3 is a matching such that if a student is assigned 2 different projects, then they get their best project, which is P4. Here as well, we have S12 assigned to P4, in M2, and S12 assigned to P6 in M3. But in M1, she's assigned to P6. That means that S12 prefers P6 to P4. Yeah. And then the join, which is the worst one. So if we join M2 and M3, we get M4. And that's because each student here gets the worst of their projects in M2 and M3 joined in M4. So this is the nice relationship between all of these 9 stable matchings we have here. And we can immediately see how, it goes down all the way to the worst matching for the students, which is M9, but it's the best for the lecturers. I'm not going to be getting into the details of that now. But how does this structure help us? What does this hash diagram, what can we do with it? For the stable marriage problem, which is the 1962 problem, because they were able to prove that this structure exists for all the set of stable matchings, so many other problems became easy to solve. And some of them are counting all stable matchings, generating all stable matchings, finding all stable matchings, and finding all stable matchings that satisfy some optimality criteria. And these are some of the papers where these problems has been solved for the stable marriage problem. But it remains open to explore them for SPIRES, because I've only just proved that the structure actually exists for SPIRES. So this is all for SPIRES, and I think I have 3 more minutes. Maybe that's all I'm going to throw at you in terms of theory and results. I've talked on SPA-P, I've talked on SPA-S. I think the final thing I want to talk about is the case where the preference lists are not strictly ordered in SPA-S. For example, a student might be unsure between 2 projects, and they would maybe prefer to tie them together if they are uncertain whether they prefer one to the other. And this leads to another problem entirely. In fact, in this case, where student 1 is indifferent between project 2 and project 1, there are 3 different types of stable matchings that can arise. And the first one is weakly stable matching, where if a blocking pair wants to occur, then both the student and the lecturer must be strictly better off. And the second one is strongly stable. What that means is if a blocking pair wants to occur, either one of them is strictly better when the switch happens, and the other is no worse off, or the other way around. And the last one is the super stable matching, where it's possible that when a blocking pair occurs, that the student and the lecturer are both indifferent between what they are currently assigned to and what they want to move to. So those are the 3 different stable matchings that occur, the 3 different definitions of stability that occur when ties appear in the preference list. And again, in my thesis, I designed polynomial time algorithm for super stable matching and for strongly stable matching. Weakly stable matchings, finding maximum weakly stable matchings are NP-hard, and that the polynomial time algorithm for that was designed by Francis Cooper, who is a student, a colleague. We both graduated this year, which is amazing. She's now working for Google. Yeah, so this is all on SPA ST. The remaining details can be found in my thesis. But something interesting I want to mention before I finish my talk is towards the end of my PhD, I was, scraping the internet, looking for papers, trying to tie up my literature review. Then I came about this paper where the student project allocation problem, all of the algorithms existing for the student project allocation were being applied in, this application where users seek to be assigned to networks. And this is in wireless networks. And it was just very nice to see that the application of student project allocation goes beyond the the natural allocating students to projects in university departments that it was initially modeled for. So this was nice. I saw the application of SPA-S, SPA-P, and SPA-SP. But then again, earlier this year, I realized that it's not just the SPA algorithm that is being applied in wireless networks. It is actually all of matching theory that is being applied in wireless networks. All of the algorithms that have been designed, the stable marriage, the stable roommates, the house allocation, all of it has application in wireless networks. And this is because of the ever increasing rate of wireless and networks, the traditional way of allocating wireless resources to wireless networks to resources is no longer feasible. And they realized that the theory fits very nicely into matching theory. And because matching theory is a very well-studied area with polynomial time algorithms and lots of exciting variants, they've just been adapting so many of the matching algorithms to wireless networks. Like the day I saw this book, I think I was awake till like 11 or 12, just reading, flipping through, trying to see if I can come up with lots of open problems, which I did. And I've reached out to colleagues in engineering departments in my school, and I'm hoping that there'll be some collaboration going on very soon. Who knows, there could be other exciting matching models to design or to come up with based on the applications that are existing in wireless networks. So that's all from me. Thank you very much, and I'll take any questions you have.
Yeah, thank you so much for your talk, Sofiat. Maybe we can all unmute ourselves and thank her for a great talk.
Thank you.
That was very informative. Yeah, and if anyone has any questions for Sofiat?
I have a question. Sophia, could I ask you to go back to slide number 23, please?
Of course. Why did I think no one would ask me a question?
Because you haven't given a seminar in this series before. I always ask a question.
Awesome, that's good. Slide 23.
Yeah.
Okay. Oh, this.
Yeah. So maybe you said this and I missed it, but I'm curious what the intuition would be for why the efficiency of the approximate solution is increasing as the preference list length increases. It seems to me that's a harder problem as the preference list length is going up. Why do the approximations get better? Do we know?
Yeah, I'm not sure I said that. I think it's the fact that there is more options for the students to apply to projects. For instance, for the 3-on-2 approximation algorithm, the format of the approximation algorithm is that when everyone applies to a project and they've been rejected up to some point and maybe the algorithm is about to terminate, then a new set of applications begins and some students are promoted. Students that have not been assigned to a project get promoted and they apply to all the projects from the beginning again. So I would say naturally, if students have more projects in their preference list, then that would mean that more choices of, more options for them to get at least one project. But then if they have just 2 or 3, then it could be restricted. Does that make sense?
Well, yes, it looks like there's two different things going on at the same time. There's the dip from 2 to 3, and there's the increase from 3 onwards.
Yeah.
So it seems there's two competing effects going on there.
Yeah, I try to. I mean, you see so many interesting things experimentally that you just can't explain theoretically. Yeah. So many of the results I had, I just had to accept what I saw. Some of the inference, it was difficult to, come up with a justification for why it was that way, without trying to pull on unnecessary strings or trying to be fishy. Yeah, but I would say that if the students have more projects on their preference list, then it just means that there is a potential that they will get assigned. And if they don't have, if the preference lists are short, then that would mean that it's going to be difficult to place them somewhere.
Okay, thank you.
Thank you. Thank you for your question. I always get questions on my experimental slides. Thank you.
I have a question.
Okay.
This is not about your experimental slide.
Okay.
So this is about your NP completeness proofs.
Okay.
So you were able to show that the problem is NP complete. Whoops.
No. Which of the problem?
So yeah, so you were able to show that some of your problems were NP complete.
NP hard, actually.
Yeah, NP hard under some with some restrictions. So if you have
Yeah.
lists of size 3 and so on.
Yeah.
Lists of size 3 and I don't remember what was capacity 1.
So if each project and lecturer has capacity 1, this is known from the literature. And if the preference list are of length at most 3 and there are 2 lecturers involved.
Yeah. So the question I had is, were you able to, if you combine some of those things to make it even more restricted, like, you know, have short preferences lists and short capacities and so on? Can you still show it's NP hard, or was?
Yeah. So for instance, when we showed that if we have two lecturers, that the number is the problem is NP hard. It was in addition to each project and lecturer having 1 capacity.
Right.
So if each project and lecturer have 1 capacity and there are just 2 lecturers, then the problem remains NP hard. So we combined those.
Okay.
Yeah.
Oh yeah. Okay.
Yeah. And I think I'm not sure, but if each student's preference list is of length at most 4, but I'm not sure what the constraint is on the lecturer side, but it appears to me that, you know, I tried so hard to see if I can, well, at least if there is 1 lecturer, it's solvable in polynomial time, but for other parameters, it just always trips up. Yeah.
Right.
Yeah.
Okay. Oh, that's good. Interesting.
Yeah.
Thank
In
you.
fact, for the preference list length of at most 3, each project and lecturer also has capacity 1. For all of these NP hardness proofs, each project and lecturer has capacity 1.
Okay.
Yeah.
Thank you.
Thank you. That's a brilliant question. Yeah, I've never really thought about it. It's just, I always just look for the parameters that make my NP hardness proof goes through.
Right. Yes.
Yeah.
Are there any other questions for Sofiat? Okay, I'm not hearing any. So if not, maybe we can all thank our speaker again.
Thank you all.